Good afternoon, everyone. My name is Eri Haneda, a PhD student of Professor Bouman. By the way, can you hear me okay? No? Can you hear me? Okay. Okay, Professor Bouman is traveling today, and so I will be a substitute teacher for today. And Professor Bouman is coming back on Wednesday. So today I will talk about the computed tomography reconstruction. And last week, I believe Professor Bouman covered the introduction of medical imaging modalities like CT or MRI. So today, could you zoom in the note? Yes. This is today's agenda. I will cover CT reconstruction. So there are three keys. Fourier slice theorem. This is not the reconstruction algorithm, but this is a general property of some projection. And then I will introduce two reconstruction algorithms. So one is a direct reconstruction using Fourier slice theorem. And then the other one is a convolution back projection. And unfortunately, this direct reconstruction using Fourier slice theorem, this is a very beautiful theorem, but it's very hard to implement it in real world. So most of people use this convolution back projection. But I will introduce both of them. And then I just assume the CT geometry is a parallel beam geometry. So I think Professor Bouman talked about fan beam geometry last week. But parallel beam geometry, this is the older generation CT. So, okay, this is... So there is some object. Maybe I should check. And this is a detector. And parallel beam is basically just beams are parallel. And then we acquire the data on this detector. And then we just change the angle, and we keep collecting the data. And on the other hand, fan beam is there's a source, there's an object, and then this is a detector. And then, okay, this is parallel beam. This is a fan beam. So I think Professor Bouman talked about this fan beam geometry last week. But in this lecture, we just assume we use this parallel beam CT reconstruction. Actually, this is the first generation CT geometry. Actually, how it works is there's one source here and one detector here. And then we get data and just move like this and keep just taking the data. So, okay. Little bit here, let's refresh the memory about the CT projections. So, first of all, many medical imaging systems can only measure the projections through an object with density fxy. And then we are looking at this line, angle theta, and this is the object. And then actually, here this looks like uniform, but it doesn't have to be uniform. The density can be varying values. And then onto a line with angle theta, we take a projection in this direction. And then we get this P theta R. So this is the projection. This is the measurement we get through CT. And actually, in reality, this is not actual measurement we get. What we get is attenuated number of photons instead of this number. But we can easily calculate this projection from those attenuated photon counts. So, okay, here, let's say, for example, this value corresponds to the integral along this line. And then this forward projection P are known as a radon transform. So if you hear the term radon transform, this means just projections. Okay, this is just review from the last week. And then first, we want to introduce a theorem, which is called the Fourier slice theorem. But before I introduce the Fourier slice theorem, I want to introduce some backgrounds first. Okay. By the way, I think I skipped most important thing. Okay, the objective today is, okay, we have this P theta R. This is the measurement. Our goal is we want to reconstruct this fxy from this measurement. That's our goal. So before I introduce the Fourier slice theorem, first I want to introduce our coordinate rotation. And then first, I think most of people are familiar with this matrix. Okay, now we are on the page 10. I think Professor Bouman finished up page 9 last week. So, okay, so this is the counterclockwise rotation matrix. And then we define the new coordinate system, RZ, like this. And what does this mean? So geometric interpretation is like this. So let's say we are looking at RZ coordinate. Let's pick RZ equal 1, 0. Okay, so we are looking at this point. This is 1. And then let's calculate this xy. Then just we substitute this matrix here. Then what we can get is cosine theta and sine theta. Okay, so what we get is just we change the coordinate. So this point now we can measure on xy coordinate. So this is cosine theta and sine theta. And the inverse transformation is just opposite. This transformation is just rotating transformation. So inverse is just we rotate in opposite direction. So basically we just plug in minus theta to this matrix. If we plug in minus theta in this matrix, then we can easily get the inverse transformation. So that's the coordinate rotation. then what we really want to do is we want to find the equation to express the projection. So we consider integration along projections. So first, we consider the function fxy. Actually, this is original image. This is original image value. And then we compute the projections by integrating along z for each r. So we are thinking about this line with angle theta, and then we take projections. Then, if we calculate the projection integral, the equation is like this. Okay. So p theta r equal, we want to take an integral along z direction. We take integral in this direction. And then we want to take an integral, but unfortunately this fxy value, we can access the image value only through the xy coordinate. So we have to change the RZ to xy coordinate values. So we transform RZ to xy coordinate values. So we have to multiply a theta. And then if we write it down, this equation, we can get this equation. So this is the equation for the projection. And this projection is also called Radon transform. And here's the next page, but this is same equation. So the Radon transform of the function, so projection of the function is defined as p theta r, and the equation can be written like this. And then geometric interpretation I explained before, but it's same thing, just like we take projection onto a line with angle theta. And then one thing we have to note is origin on xy coordinate is mapped to 0 along r axis. This is our assumption. Okay, so now we are ready to study Fourier slice transform. Okay, what is the Fourier slice theorem? Sorry, not transform, theorem. The Fourier slice theorem is page 13. This is the theorem. Actually here, like, they show the conclusion first and the proof comes later. So, okay, before talking Fourier slice theorem, we define two equations first. And then we will see these terms a lot later, so please remember this in your brain. So first, this p theta r, this is a projection we take on a line with angle theta. So, okay, this is projection. Okay, and then we define a CTFT, continuous time Fourier transform of P, and then we define this as a capital P. And this is a 1D Fourier transform. And second, we take a 2D Fourier transform, continuous space Fourier transform of fxy. Fxy is the original image. Original image. Then we define the 2D Fourier transform as a capital F, FUV. And then the Fourier slide theorem tells us then this relationship satisfies. This is a very simple equation, but it means a lot, and it's very confusing. But I will explain it using the diagram soon. But the Fourier slide theorem tells this capital P theta rho equals FUV in polar coordinates. By the way, here, this equation using the term rho, this is just a frequency variable. It's very common to use small f for this, usually. But in this material, f is already used to denote the original image, so it's confusing. So just they are using rho instead of f. So this is frequency variable. So okay, what does this equation means? Actually, it's much easier to understand this equation using a diagram. So here's the diagram I drew before the class. Okay, first, we are thinking about this side first. So this is a plot of fxy, original image. And then I'm considering the line with angle theta. And then I take projection, and I call it P theta r. And then we take a 1D Fourier transform of this signal. Then we will get something. We will get some 1D signal, like as a Fourier transform of this. So it's denoted by capital P. Okay, meanwhile, in the meantime, let's forget about this. Okay, let's go back to my original image, fxy. We take 2D Fourier transform. Then we get some plot of FUV in frequency domain. And Fourier slide theorem tells us actually these values exactly match to the value on the line here, on the line with angle theta. So if we get FUV, if we draw a line with angle theta, these values on this line is exactly same as this Fourier transform of the projection. This is a little bit mysterious, but it is. So this is same. These values on this line exactly match to these values. So actually, if we slightly change the theta and just we do same thing, we can plot values on this FUV coordinate. So that means we can calculate the values on FUV. So actually, if we can take inverse Fourier transform, actually we can reconstruct fxy. Does it make sense? Yeah, so, okay, let me draw one sentence. So summary. The Fourier the Fourier transform of projection p theta. Sorry, this is small p at angle theta is a slice of FPB through the origin at angle theta. So this is what Fourier slice theorem tells us. Actually, if we write down the theorem, just this one equation, but what it actually means is this. And I think it's easier to understand it through the diagram. Okay, so actually next 2 pages explain about the proof of this Fourier slice theorem. And actually this material shows 2 different proofs. And the first one is just plug in, and you can do it method. And the second proof is more simpler and more compact. So I will do quick review of the first proof, and then I will move on to the second proof. So page 14, this is proof number 1. Okay, so what you need to do is just plug in. So first, by definition, p theta r can be described like this. We already saw this equation in the previous note. Just definition of the projection. And then next we take a CTFT of this P. So this line is just we apply the definition of the CTFT. And then what we do is just we plug in this equation to here. And then we can get this equation. And then from here, just we swap the order of each term. And then we can get this equation. And then from this line, what we want to do is actually we want to change the variable ZR from ZR to XY for the proof. So we use the relationship equation between XY and RZ. And actually, to change the variable of ZR to XY, we need to use calculate the Jacobian here. And actually, A theta is just a 2x2 matrix, so it's relatively easy to calculate this. But just in case, let's calculate. Y Jacobian equals 1. So right now, okay. We have this relationship, and okay, A minus theta is minus theta cosine theta. So basically what we want to calculate is EL dV we just want to calculate this part. And then if you look at the calculus book, like the definition of this is basically like this. And then actually, because we already know this matrix, so R and Z can be expressed as a function of x and y here. So we just need to take a derivative here. Then we can get very simple equation. And then just take a determinant, and then you will find this equals to 1. So calculation is not so bad. This is because 2 by 2 matrix. Okay. So we knew that Jacobian is 1. So just we change all of the variables from RZ to XY. And then I think most of people are familiar with this form of this equation. This is a Fourier transform. So this is a Fourier transform of fxy, but just x, this uv value takes a value rho cosine theta and rho sine theta because of this. And this is the end of the proof. So this is the first proof. So basically what we need is just keep plugging the variables. And actually the second proof is more compact, simpler, and maybe more beautiful, probably. If somebody asks you to prove the theorem, maybe you might want to use this one because it's easier. Okay, this is proof number 2. So this one, just we prove one of the case of the Fourier slice theorem. So we consider the case theta equals 0. Okay, if we consider theta equals 0, then projection can be expressed as this form. The reason is like this. Okay, right now we are consider theta equals 0. Okay, theta equals 0. So we have an object. So actually this is x, this is y. But we are considering the line with angle 0. So this axis R, actually it's same as x. So that's the reason why x is replaced with r. And then we take a projection along y-axis. So we are taking actually integral over y. So for the theta equals 0 case, projection equation is simplified like this. Then we take a Fourier transform of P. This is just a definition of Fourier transform. And we plug in this equation to here. And then we reach this form. And actually, again, we are familiar with this form. This is a form of the Fourier transform of fxy. Actually, r is a dummy variable, so it can be anything. It can be x, it can be any other variable. So, okay, this is the Fourier transform, fuv, but uv takes the value of rho and 0. Okay, so we get for theta equals 0 case, P rho equal F rho 0. What does this mean graphically? Okay. So let's say we have a FUV. Then what does this mean? This means actually V always equals 0. So actually this is this line on FUV. This line. So what we did is that we just proved one of the case theta equals 0. If we take a projection on theta equals 0 and then take Fourier transform, then it's matched to the value on the line over here. Okay, then we proved one of the case. Then by rotation property of Fourier transform, it must hold for any theta. What does it mean? This means so rotation property of CSFT is like this. For example, we have some fxy, and then there is some corresponding Fourier transform something. Okay, and the rotation property says if we rotate this fxy with a certain phi, let's say, then the Fourier transform of fxy also rotates with the same amount. That's the rotation property. So if we use this property, we are done with the proof. Because, for example, okay, okay, this is a fxy, and this is a FUV. And we already know if we take a projection onto this line and then take Fourier transform, we already know this value on this line matches to this line on FUV. And what I want to know is, what if we change the theta? For example, we want to take a projection onto, okay, this line, let's say phi. Then what we can do is, okay, look at this, and then rotate object so that this line matches to the axis x. Then this map to the value of the rotated frequency transformation line. So that means the Fourier transform of this projection matches to actually here. And then, you know, this, like, we can say same thing for any angle phi. So proof is over. So actually, in this proof, we just need to prove only one case. So that's the end of the proof. Okay, so we finish up the proof of Fourier slide theorem. And let's go back to the original part. Okay, why Fourier slide theorem is so important? We already learned, okay, if we use this theorem, we can plot FUV. And if we take inverse Fourier transform, we can reconstruct original image, fxy. That's very nice, beautiful. But the life is not so easy. And then, actually, if we use this method, there are many technical challenges to implement it. Why? Actually, we can see challenges, actually. Okay. Using Fourier slice theorem. Actually, computer can handle only discrete values. So what we can do is, we want to plot FUV using the projections. So, okay, I can calculate, and then we start plot like this. Okay, then I change the theta a little bit, and then I can calculate Fourier transform of projection like this. Okay, so I just can continue, and then we can plot everything. However, next step we take is inverse Fourier transform from this capital FUV to FXY. To implement this inverse Fourier transform, what we really need is data on rectangular grid, like this. To implement the inverse Fourier transform, what we need is data on regular grid. So this point doesn't match to this one. So actually, we have this data, but we really need is the data at the location of circle. And then to get the data on this circle location, we need to do some kind of interpolation using this cross-out data. Like, you can use anything, but actually this costs a lot, like computationally expensive. And plus, look at this. Around the origin, the data is very dense. So probably, even if we do interpolation, probably we don't have problem. But if we look at these two lines, if R is getting larger, these two lines getting far away, right? Like this. So, like, if you look at the data far from the origin, the data are very sparse. We don't have many data. So if we implement interpolation, maybe we don't get good accuracy. So that's another problem. So maybe in the real reconstruction, probably we can get good reconstruction in higher frequency domains.
Excuse me.
Yeah.
Why do we have the rectangular box for circle?
Actually, this is just the way like inverse Fourier transform is. Just to implement inverse Fourier transform, we need these like equally spaced samples in rectangular grid. Yes. So yeah, there are many problems. Actually, this Fourier slice theorem is very beautiful, but we have some challenges to implement this. So most of people don't use this direct method. Instead, most of people use this algorithm, which is called convolution back projection. Some people call like forward back projection, either way. So actually, if we use convolution back projection, we don't need any calculation in frequency domain, actually. So it's computationally quite fast. And then this algorithm is a little bit complicated. So let me show the summary first. So without thinking any theory behind it, I will just tell you how to do it first. So convolution back projection is like this. So first we measure the projection onto a line with angle theta. and then we filter the projections. Actually, this filter is a high-pass filter. I will explain why later, but anyway, we apply some kind of filter on this projection data. And then after we apply filter, we do a back projection. Okay, what's a back projection? Back projection is like this. Okay, let's say this is a filtered signal. This is origin. Then what we do is we smear out like this. It's like a windshield wiper of the car. So okay, we have this function for some theta, and then this, for example, this line, all of the points on this line takes this value. All of the points on this line takes this value on g theta r. So basically, we kind of paint like this. And then we slightly change the theta, and then we sum up. We do same thing. We smear, change the theta, and we do same thing. We smear out like this. Then we get the original value. This is a quick overview of the procedure of convolution back projection. But we haven't studied why this works. So I will explain why this works. Okay, so I will go back to previous page. Okay, if we look at this algorithm by equations, it's a little bit complicated. But if we draw diagram, it's not so bad. Okay, first, actually I want to add two lines here. Actually, this UV and rho theta, this came from the Fourier slice theorem page. So first we define UV like this. So basically it's UV. And if we take some point, this length is rho. And this is theta. Okay. And then we can easily calculate du dv equal, this is a Jacobian, like what we did before. We can easily calculate this term. And then what we want to do is, okay, we want to find this fxy. We want to reconstruct fxy. So we take a inverse Fourier transform of this. So it's inverse, so there is no negative here. And then we just change the variable from UV to theta and rho. And so we just plug in this one. Actually, I'm sorry. This is actually this equation little bit absolute value is little bit messed up, but okay. Let's ignore this one for now. And then here it's a place Fourier theorem plays a role. So FUV, actually if we plug in this relationship here, and then if we apply Fourier theorem, it became this term. And then we little bit swap the term, and then we get this equation. Actually, it's a very complicated equation. So currently, we don't know what this means. So let's simplify a little bit. Okay, first we simplify this part. We define this part as a g theta, x cosine theta plus y theta. This is because we take an integral over rho, right? So this variable rho goes away eventually. So just this part just remains. And then, okay, what's this? First of all, what's the function of g theta? G theta this is a filtering part. So if we write down g theta, it's like this. And then again, we are very familiar with this form. This is a form of inverse Fourier transform. So inverse Fourier transform of this absolute value rho and capital P. So this is the CTFT of the projection. So they are doing something here. And actually, if you write down this absolute value of rho, it's going to be like this. Oh, sorry. Okay. Right. So this is actually high-pass filter because they are cutting the low frequency component. So actually, they are doing high-pass filter here. And then multiplication in frequency domain is convolution in spatial domain. So that's the reason why there is a convolution. So basically, G is just filtering with high-pass filter. And then another thing. Okay, now we know what's going on G. Then what is the other part? This is what I explained. Actually, x cosine theta plus y sine theta. This is actually inner product of xy and cosine theta sine theta, right? Okay, so maybe this one. Okay, so this is an inner product of xy and cosine theta and sine theta. So actually, if we ignore this integral part, like let's think, what's the shape of this function? Actually, we can write this function using some contour. So let's assume this part is equal r, and then actually we can draw contours like this. So this is a g theta r, and then these are the set of xy which satisfies this equation. Let's say here this is r. Then we can write down the contour like this. And then we take an integral over all of the theta. So basically this operation is just smear out and smear out, sum up, smear out, sum up. So that's the way it works. And actually, the next 2 pages just more details about this. And there are some examples on Professor Bouman's website too. So you can take a look up actual image on his website.